Whoa, did you see that? The sock fell because I turned on the fan. But why? Let me explain. There are laws that help us understand exactly how things move or sit still, like why you don't float out of your bed or fall through the floor of your house. These laws are more commonly known as Newton's laws. The first clip we saw was an example of Newton's first law, the law of inertia. It states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an outside unbalanced force. In the clip, the sock is at rest, with no unbalanced forces, but because we turned the fan on, that introduced the outside unbalanced force, causing the sock to move, then falling to the ground. Another example is when I push my hydro flask. Right now, my hydro flask is not moving, nor does it want to, but because I push it, that introduces an outside unbalanced force, causing it to move.
Hey everyone, I'm going to be explaining the second part of Newton's first law. An object in motion will stay in motion unless acted upon by an unbalanced outside force. To explaining this, I'll use this cup. This cup's water doesn't spill when I slide it side to side, but when I abruptly stop it while it's sliding, using the force of my hand to stop it, water does spill out. And that's because while I'm using my hand to stop the cup, I'm not using my hand to stop the water, so the water comes out of the cup because its motion is still unimpeded. Come here. Now, for my second example, I'll use this board with this cup on it. This board's going to ram into that pillow, and when it rams into the pillow, the cup moves forward. And that's because while the board's motion was impeded by the pillow, the cup's motion was not. So, its motion continues on. Alright guys, I'm going to be showing you Newton's second law of motion. Force equals mass times acceleration. To do this, I set up a little experiment. This red Solo cup is going to absorb the force from this little ball connected to a string, and we're going to be measuring the amount of force that gets put into this cup with these lines. Farther it goes down the line, more force is applied. And this will just help me keep my acceleration constant, because I'm going to be dropping it from parallel to the desk. Now, let's test it out. Doing that, we got about 3 lines in. Now, we'll do the same thing, but this time I'm going to add a little oomph to the acceleration by throwing it down a little bit. And by doing that, it went way farther than the lines. Now, I'll prove the mass part of the law. By doing that, I'll add some more mass to the ball. And we know that without any acceleration added, it'll go up to about 2 lines. But with just mass added, it goes past the line again. And since this is my last part, I'd like to thank Sir Isaac Newton for this blessing that I'm able to do this video with you guys. Alright, bye.
Newton's third law states that for every action, there is an equal and opposite reaction. This means that when I hit something, like a wall or someone's face, the wall will hit back with the same amount of force, and the person's face will hit back with the same amount of force. In this clip, as I put my hand on the wall pushes back on me. Because of this, the forces are equal and there's no acceleration. Here, my binder is on the table. Because the binder is pushing on the table pushes back up on the binder, causing equal forces and therefore not acceleration. However, in this clip, more of the binder is off the table than on. This then causes the binder to fall downwards. Because there is no force to oppose gravity, this causes the binder to accelerate downward. Thank you to Sir Isaac Newton for allowing us to understand motion.